Hey guys, so this week we're going to be talking about designing our own type classes. So kind of as a consequence of just being able to use Haskell because of the default types that pop up whenever you use like plus and stuff, you've been introduced to type classes basically since day one. However, to this point, we've never really focused on how to design our own type classes, when to do it, and how to do it. So before we get into that, let's do a review of how types work inside Haskell. So let's go right back to the first tutorial. So what are the types of the following functions? So obviously num, this takes an x, okay, and then it adds 1 to x. So the key here to realizing, well, what is the type of x going to be, is that x is used with the plus operator, and the plus operator is part of the num class. So if we copy this, then put it into Haskell here, and this of course gives us our type right away. Obviously num is going to be a num a goes to a. Okay. Notice the equals. So the trick is once again noticing that this equals is part of a type class. So it's part of the EQ type class. So x and y, if we're using that with equals, x and y are going to have to be members of the EQ type class, and then it just returns a char. So if we paste this in, equals is going to be an EQ a, okay, they must be the same a because we're comparing them to each other, and it returns a char. Fractional anyone? So fractional anyone, there's a trick here. So times is part of the num type class, just like plus. Okay, so you might think, well, f must be the num type class, but then we have this division here. So the division isn't, it's a part of the num type class, it's part of the fractional type class, okay? And it ends up being just fractional. And now the trick here is, let's actually open up a terminal, and let's load this back, GCI source. Okay, so let's use this info function to get some info of what's going on here. So let's try info of times, and we'll see, oh look, multiplication is part of num. Info of division, this is part of fractional. Now you'll be like, well, how come this is a fractional a instead of a num a? Well, the trick here is actually that the fractional class, in order to be an a fractional, it also has to be part of the num class. So we don't have to specify num here for specifying fractional. If it's a fractional a, it must also be a num a. And then we get this use of times for free. Okay. Now finally, the last weird one here is kind of just 1. 1 equals 1. What type would this be? This one might actually surprise you a little bit. Okay, the default type it gives here is integer, but actually you're fine saying this, that 1, this literal 1, could be any num a. Okay, so the trick here is that when you're writing these literals like 1, 2, 3, 4, okay, they should be able to default to whatever type num type you're using at the time. If you're using it in a context that's let's say you add 1 to 2.0, okay, then it becomes a fractional. Then 1 becomes a decimal number. Okay, so this is a little bit of a weird thing to get over, but it's actually it's a pretty neat, pretty nice feature that Haskell gives you, because you don't have to go around choosing, oh, do I write 1.0 or do I just write 1 here? Because it does the work for you. It makes it by default just a member of this type class. So what do all of those functions have in common? They're overloaded. So what's overloading? It's kind of like having polymorphic functions, but there's a little bit of a difference. So length, for example, is a standard polymorphic function. So you're just saying you have a list and you want to find the length of the list. And the reality is the type of the things inside of that list don't really matter. When you're defining the function, you never use it in a way that it matters. So you can just say it's a list of any a. and this makes it polymorphic. But overloaded classes, on the other hand, okay, they're going to depend on some sort of class constraint. Okay, so actually, to go back, each of these you can tell they're overloaded because you're saying, well, this depends on a class constraint. It depends on num A or equatable A. Okay, so they're overloaded. We would actually say that these would be the standard overloaded functions. This is the standard way of looking at it. So equals equals is an overloaded function because it has different definitions for each type. Okay, so for bool, equals equals is defined one way, and then for maybe, equals equals is defined another way. Okay, so it's different than just being like, well, this is defined the same way, but it works on many different types. What you're saying is this is defined a different way for each type it's made over. So we call that overloaded. So in Haskell, we define overloaded functions through type classes, and there's two elements to type classes. There's the interface definitions and there's the instance definitions. So let's start off with the interfaces. So a interface, okay, will specify a collection of type signatures. So when you write the interface, you only write the type signatures over a type parameter. So every class, you say class, you give it the name of the class, and then you give it a type parameter. So it's like you give it a variable, which is a stand-in for a type. Then you define which functions, you could also call these methods. So which functions or methods that are associated with this class, and you just give their type signatures. And usually you're going to use this type parameter inside the type signature. So there's a type class, functor, okay, that implements map. For some reason they use fmap over different data structures besides lists. Okay, so we did this in previous tutorials where we tried to implement map over our own list data types and on tree data types and stuff like that. So it makes sense to have an idea of mapping over many different data types. So what we do is we use f as a stand-in for whatever data type we have, and f is going to be a data type that takes another type parameter to it. Okay, so this is, instead of writing list of A here, we write f of A, and instead of writing list of B here, we write f of B. So fmap, it takes a function from A to B, some type wrapping around A, and some other type returns some other type wrapping around B. So the instances, so we make this definition, this interface, so class interface, and then later on we go and we write instances and we write how fmap is defined depending on what type we give it. Okay, so we have to give it a type that takes a type parameter. So let's keep this in mind. So recall, I'm going to import preload, and I'm going to hide these things. Hiding maybe and either. Okay, so recall the maybe type. So maybe A equals just A or nothing, right? And we're going to hide functor as well. And we drive and show just so that we can print it. So then we could have maybe either A, B. Okay, so this actually has two, equals left A or right B. Okay. Okay, and then we could also have, let's compare this to another type. So data, colors, red or blue or green. Okay, and then if we had our functor class, so class functor f, where we have our fmap type. So fmap A, B, f of A, f of B. So you have to notice that the crucial thing to notice with the functor type class is that f here takes a type parameter. So let's say we tried to make an instance of functor colors. And we tried to make fmap f, and we have some colors, and we'd be like, we just always return red. This is going to give us an error. Why? So it's going to say expected kind. So this kind is kind of like the type of types. Okay, this is a bit of a weird thing to wrap your head around, but saying star to star. So the type of types, it's always just going to be some combination of stars, at least for simple types. And what it's basically saying here is that it's expecting something that takes a star and returns a star, but colors just has star. So really all it's saying is it's expecting a type that has one type parameter, okay, because it's used that way. It's like f of a, f of b, but colors doesn't have any type parameters, so that's no good. We can't do that. Now maybe on the other hand, it does have one type parameter, so that works just fine. We can say fmap maybe, and the way you want to define fmap for maybe is when you have just x, then that returns just f of x. You apply it to the thing inside, and when you have nothing, you just return nothing. So fmap actually is we actually have to hide just and nothing. Okay, so fmap actually is defined for the default nothing in prelude. Okay, we're hiding all this stuff, but this is how it's defined. This is how it makes sense to define mapping over maybe. Now, what about either? Okay, either is a bit of a trickier one. So the trick with either, okay, we might be tempted to say instance functor either where, okay, but this is the same kind of issue as before, except so before it was like with colors, well, it doesn't have enough type parameters, so there's nothing that we can do. With either, it has two type parameters, okay, and we want something that only has one, and you can tell by this kind thing here. So there is a trick though. What we do is we could make a functor for either a, so it's like we give it like an implicit type argument here, okay, and the way we would do this is so either is going to be either left, so we're going to have two scenarios here, left x and fmap f right x. Okay, so there are these two scenarios, and what you might be tempted to do is right, okay, so left, then you map f to x, and right, then you map f to x. Now the problem with this is that either a, like if you look at what's going on here, fmap's definition here, okay, it's the a goes to b is going to be only for the second type parameter of either, okay? When we're writing that it's either a, right, this a has to stay the same. So the left part here, this left a, we can't change it. We have to leave it alone in this case. And then we only map over the right part here. And then same thing as before, we have to left, right. Okay. So this way, we have a valid functor definition for either as well. So now you might have a bit of an idea of how to implement type classes and their instances, but you probably don't quite understand yet why you would want to make a type class and its instance. So for that, let's go through this little case study. So a vector space is something from mathematics, and it's used, the way it's used in mathematics actually reflects how you want to use it in Haskell in a lot of ways. So a vector space, it's a collection of functions that would need to be defined differently given a different vector definition. So in math, we use vector spaces so that we don't have to keep writing theorems over and over again for, like, let's say the complex numbers and the real numbers and the 2D vectors and the 3D vectors and stuff. We want to write these theorems and be like, oh, I can prove these theorems for any of these things, anything, as long as it's a valid vector space. So a vector space, if we were to try and code it up in Haskell, what we would basically do is we would create the following functions. Okay, we would have some vector type, and that vector type would have a 0. It would have a scalar product. Okay, it would sum things. There'd be some way to sum them together. There'd be some way to take a magnitude, and this is actually not part of a vector space in general usually, but generally vector spaces also have an inner product space. They have this idea of this inner product operation. So the trick here to realize is that if we have these functions here, then many computations can be implemented regardless of the underlying vector type, just using these functions. You can just use these functions directly, and the underlying vector type shouldn't matter. They can be generalized over this. So if we want to make a library that takes advantage of this generalization, what we're going to do is we're going to put these functions into a type class. So step 1 is going to be to create this vector type class. So we move to VS Code, and we're going to define this class, and it's going to have each of these operations. So notice we only put the type signatures right now. That's all we need at the moment, is the type signatures of each of these operations. Now for step 2, what we're going to do is we're going to create a data type. Let's call this one, we'll start off with vector2. Okay, so vector2, it's going to be a vector, okay, 2-dimensional vector that's basically just kind of a tuple. And now that we have this data type, what we need to do is we need to make an instance of vector space for this data type. So we need to be like, well, how are actually each of these functions defined for this data type? So we'll write instance vector space vector2. Okay, and now we need to define each of these things. So what is the 0 type look like? Okay, so we need to follow its type signature. So 0 returns a vector A, okay, where A is any num type here. So this is going to be a vector2, 0, 0. Okay, now what about vector sum? So vector sum is going to take 2 vectors. So we're going to have this pattern match. Vector2, x1, y1. Okay, vector2, x2, y2, and it's going to add those together. So how are these going to be added together? Well, it's going to return another vector2, x1 plus x2, y1 plus y2. Okay, vex scalar product. How are we going to do this? Well, vector scalar product, the way we're going to define this is going to take an A, okay, so just some S, and then some vector of A, power match again, vector2, xy, and it'll return a vector of A, vector2, S times X, S times Y. Okay, so what it's doing is it's taking this num A and it's multiplying it on the inside of the vector, the contents of the vector. The magnitude, so now we have a floating type here. Okay, so the magnitude, vec magnitude, it's going to take a vector, power match again, vector2, x, y. Okay, and the magnitude of a vector is going to be the square root of x times x plus y times y. Okay, and finally, the vector inner product, we have to define the inner product operation. And what we'll do is there's different ways you can define inner product according to math. We'll do the Euclidean math thing, okay? Oh, and we take two vectors, sorry. So it's vector 2, 3, x2, y2, and this will be x1, y1, and its definition, okay, is going to be x0 times y0 plus, sorry, x1 times x2 plus y1 times y2. Okay, so this is the standard Euclidean inner product here. And does it return the right type? Should. Oh, I spelled it right. Wow. Back inner prod is how I spelled. Okay. So now we have a class, and we have an instance of that class for one data type, for this vector2 data type that we defined here. So we kind of divide up what we're doing here. So it's like we have our type class interface. Okay. We have our instances. Okay. This is our data types. And now finally, okay, why are we doing this? Well, we're doing this so that we can make our library, okay? And these libraries are going to be generic to any type class instance, to this type class. So let's think of some of the things we could do with this vector type class. So if you were building a library to work with vectors, there's all sorts of operations that in general should just work out with any vector. So let's say taking the difference of two vectors. Okay, so the way you'll write this is you'll specify them in terms of their type class, okay, your arguments. So instead of being like vector2 here, you'll write, well, this is anything that belongs to vector space and has a num type. It's a VA and another VA and returns a VA. Okay, so this will take the difference between two vectors, any two vectors, and we'll write this. The trick is now we're going to write this in terms of these functions. So we could write vec sum v1. So the difference is going to be the sum of the first vector and the second vector, but negated. So what we're going to do is we're going to negate the second vector and add it to the first one. Okay, so now we have a vec difference. We could have a vec distance. It's going to be largely the same. So the distance could be a v1, v2, and what we do to take the distance is we take the magnitude of the difference of two vectors. Oh, and this needs to be a loading type now. So keep in mind that, okay, almost got this wrong. So keep in mind that the vec magnitude, okay, up here, uses a floating a. So that needs to be a floating a instead of a num a here. And then we could also have vec max. Okay, we could find the maximum vector. So if we have vector space v, floating a, portable a, VA, and we have a list of VA, return VA and an A. So basically, we're going to find the vector with the maximum distance out of the vectors out of this list. We're going to find the one with the maximum distance from this first vector. So how can we do that? Well, we could use fold R, okay? And what we'll do is for each vector, we'll create a binary operation and a vector with some distance. We'll say if the vector distance of v0 and v1 is bigger than the current distance that we have going on here, then we'll return that new vector distance, right, between v0 and v1. But if it isn't different, well then we'll just continue keeping the other one, okay, v2d, and we'll apply this to v0, 0, and v's. Okay, so this is just an example of a few functions. You could probably define a lot more functions. There actually is a standard kind of vector library in Haskell, and you'll see it has a ton of functions, and they all vary over a vector class rather than a specific vector. So now all of these functions work off of vector 2D, and we can then go off and be like, well, data vector 3a equals vector 3a a, right? And then we create an instance of that. It'll look pretty similar. This will be vector 3. So then now instead of here, 3, 0, 0, 3, well now it's going to have a z1, z2, okay? It'll return z1 plus z2, okay? So be turned into 3, 3, 3, z, 3, that's times z. And so this is the annoying part, is that you still have to kind of make these trivial changes, even though a lot of them are pretty trivially straightforward. But once you've made the trivial changes for just these functions, okay, set 1, okay, so after you've implemented these changes, now these functions just magically work for vector 3 as well. And then you can do the same for vector 4 and vector 5 and whatever vectors you need. Okay, and then all these functions will magically work. And if you consider that this might be a very large library, like you could write massive amounts of functions for this. You're getting a tremendous amount of code reuse by doing this. So just to reiterate the advantages of this, this code reuse stops us from having to redefine a bunch of code, and this gives us better readability for one thing, and also reduces the chance of introducing bugs. Just because you're kind of writing less code, there's less chance of introducing bugs. It also kind of just makes your code more modular, and it makes it easier to figure out what's going on for whoever is reading this. So I'm going to end this tutorial with a challenge. So try and implement an instance of the following data type for your vector space, and try and implement a function vec_sub that just works off of any two vectors that are a member of the vector space class and subtracts two vectors. So I'll leave you with that challenge, and maybe if you're feeling very ambitious, you could try even more instances of this and have fun with that, guys. Okay, see you next time. Have a good one, guys.